Let's begin with the definition of the row space of a matrix. Let A be an m by n matrix. Then the row space of A, denoted by row A, is the subspace of Rn spanned by the rows of A. So in this case, we let the rows of A be R1, R2, all the way to Rm. Then A can be expressed as the rows of the matrix R1, R2, all the way to Rn. Alright, so we can then write down the row space of A is equal to the span of the rows of the matrix R1, R2, all the way to Rm, which is given by the set of vectors C1, R1 plus C2, R2, all the way to Cm, Rm, such that C1, C2, all the way to Cm are real numbers. So in other words, the row space of the matrix A is the set of all linear combinations of the rows of matrix A. Now let's take a look at the relationships between row space and column space of a matrix. Suppose A is an m by n matrix, then the row space of A is equal to the column space of the transpose of A, where both are subspaces of Rn. Conversely, the column space of A is equal to the row space of A transpose, where both are subspaces of Rm. Now this is obvious since the rows of A are the columns of A transpose. Conversely, the columns of A are equal to the rows of A transpose. Now let's consider the linear system Ax equal to B, where A is an n by n matrix, X is a vector that belongs to the Rn space, B is a vector that belongs to the Rm space. Recall in our previous lesson on the column space, where we claimed that Ax equal to B is consistent if and only if B lies in the column space of A. Now, by virtue of the above relationships that we have just learned, we can also claim that Ax equal to B is consistent if and only if the transpose of the vector B lies in the row space of A transpose. This is because the column space of A is equal to the row space of A transpose. And why do we use the transpose of B? Because we are talking about the row space of A transpose. And B here is originally a column vector, so we have to convert this into a row vector. Now let's see how we can use the above results to solve some simple problems. Example 1. Determine whether W is in the row space of A, where A is a 2 by 3 matrix and W is a 1 by 3 row vector. We first consider the linear system A transpose X equal to W transpose. Now from the previous, we know that W transpose is in the column space of A transpose if and only if the linear system is consistent. So by point 2 above, the linear system Ax equal to B is consistent if and only if B transpose is in the row space of A transpose. You can say that W lies in the row space of A if and only if system is consistent. So in this case, we set up our augmented matrix. This is part A. First, we have A transpose, which is 1, 1, 0, 1, minus 1, 1, augmented by W transpose, minus 1, 1, 1. You can row reduce it, and it can be shown that the result would be 1, 1, 0, 1, 0, 0, and the augmented column, minus 1, 1, minus 2. In this case, the last row here shows that the system is inconsistent. Therefore, W doesn't lie in the row space of A. So we say last row shows that system is inconsistent. So this implies that W does not lie in the row space of A. So that is the answer for part A. Now take note that this is the row echelon form, not the reduced row echelon form. You do not need the reduced row echelon form to determine whether the system is inconsistent or not. So typically we stop at the REF row echelon form. For part B, the solution procedure is basically the same. So we consider the linear system A transpose X equal to W transpose, where our A transpose is a 3 by 3 matrix, our X is a 3 by 1 vector, and our W transpose is also a 3 by 1 vector. So once again, we say that W transpose lies in the column space of A transpose if and only if system is consistent. And similarly, this implies that W lies in the row space of A if and only if system is consistent. So in this case, the augmented matrix is equal to A transpose augmented by W transpose, and this is equal to 1, 0, 1, 1, 2, minus 1, minus 3, 1, minus 4, augmented by 2, 4, minus 5. This can be row reduced to row 2 becomes row 2 minus row 1, and row 3 becomes row 3 plus 3 row 1, and that will give us 1, 0, 1, 0, 2 minus 2, 0, 1 minus 1, augmented by 2, 2, 1. And then the next step is to get rid of this number 1 below the pivot of 2. So we have first convert this into a 1 to make our life easier. So row 2 becomes half of row 2. That will give us 1, 0, 1, 0, 1, minus 1, 0, 1, minus 1, and 2, 1, 1. And then the final step is to get rid of this number here. So we have row 3 becomes row 3 minus row 2. So we have 1, 0, 1, 0, 1, minus 1, 0, 0, 0, augmented by 2, 1, 0. Now the last row shows that the system is consistent. So we say since system is consistent, this implies W lies in the row space of A. So that's our answer to part B. Now let's take a look at an alternative method to solve the same question. Now if we were to append this row vector W to the last row of matrix A, then there will be two cases when we reduce it to the row echelon form. Case 1 is where the bottom row becomes a row of zeros. In that case, we say that the vector W is linearly dependent on the rows of A, and therefore W lies in the row space of A. Now the other case is when the bottom row is non-zero, which means that the vector W is linearly independent of the rows of A, which means that W does not lie in the row space of A. Okay, so for part A, our matrix looks like this: 1, 0, minus 1, 1, 1, 1. This is the original matrix A, is appended by W at the bottom, minus 1, 1, 1. Alright, and then we will reduce it to the row echelon form. Here, obviously, 1 is a pivot, so we get rid of 1 and minus 1 below. So, first operation, row 2 becomes row 2 minus row 1 to get rid of this. And the second operation, row 3 becomes row 3 plus row 1 to get rid of this number. So we end up with 1, 0, minus 1, 0, 1, 2, 0, 1, 0. Here we can immediately identify that this is the second pivot, so we need to get rid of this number below the second pivot. So we apply this operation, row 3 becomes row 3 minus row 2. And we end up with 1, 0, minus 1, 0, 1, 2, 0, 0, minus 2. So we can box up the pivots. We have 3 pivots here, in fact. We observe that our row 3, which is the appended row, originally the W vector, is not reduced to a row of zeros. So this implies that W is not linearly dependent on the original rows of A. This implies that W is not in the row space of A. Now conversely, if W were to be reduced to a row of zeros at the bottom, then it will be linearly dependent on the original rows of A, in which case W will lie in the row space of A. Now one important point is that the appended row should not be swapped with any other rows, so that we know that the linear dependence or linear independence is always associated with the appended row, which is the vector W in this case. For part B, we use the same method. We append W to the bottom of matrix A. So therefore, we consider this matrix with 4 rows: 1, 1, minus 3, 0, 2, 1, 1, minus 1, minus 4, and 2, 4, minus 5. First operation, because this is a pivot, so we have to get rid of this number here and this number here. And for that, we apply 2 operations. Row 3 becomes row 3 minus row 1. Row 4 becomes row 4 minus 2, row 1. And you end up with 1, 1, minus 3, 0, 2, 1, 0, minus 2, minus 1, 0, 2, 1. Right now, the second pivot lies here, so we have to get rid of these 2 numbers, minus 2 and 2, below the pivot. And for that, you apply two more row operations. Row 3 becomes row 3 plus row 2. Row 4 becomes row 4 minus 2, row 2. And we end up with 1, 1 minus 3, 0, 2, 1, 0, 0, 0. So also all zeros. So we conclude that since the appended vector W becomes a row of zeros, this implies W is linearly dependent on the rows of matrix A. Then this means that W lies in the row space of A. So that's our answer for part B. And once again, please note that we should never swap the last appended row with any other rows in the original matrix for this method to work. Now, why is it that we cannot swap the appended row with the other rows in the matrix? Let me illustrate the case when you actually do a swap. What will happen to our result? So now matrix A is appended by this last row, which is the W vector. So we have 1, 1, minus 3, 0, 2, 1, 1 minus 1 minus 4, and then finally 2, 4, minus 5, which is the appended row. Now let's say we perform a row swap where we swap row 2 with row 4. So we end up with 1, 1 minus 3, 2, 4, minus 5, 1 minus 1 minus 4, and finally 0 to 1. So here row 2 and row 4 are swapped, and then we proceed to reduce it to our REF. Okay, here we perform two row operations. Row 2 becomes row 2 minus 2 row 1, and then we also have row 3 becomes row 3 minus row 1. This is to get rid of this number here and this number here, because the number 1 is the pivot. So we end up with 1, 1 minus 3, 0, 2, 1, 0 minus 2 minus 1, finally 0, 2, 1. And then here we identify that our second pivot is the number 2 here. So we need to get rid of these two numbers below the pivot. And for that case, we perform another two operations. Row 3 becomes row 3 plus row 2. And also row 4 becomes row 4 minus row 2. And we will end up with 1, 1 minus 3, 0, 2, 1, 0, 0, 0. Last row also all zeros. Alright. We know previously that W is linearly dependent on the rows of A, because the appended row W becomes a row of zeros. In this case, we note that since we have swapped row 2 and row 4, so our W is actually in row 2. But row 2 ends up to be non-zero. So does it mean that our W is not linearly dependent on the rows of A? No, the previous solution already shows that W is linearly dependent on the rows of A. So by swapping row 2 and row 4 and obtaining our REF, this gives us the erroneous conclusion that row 2 is not linearly dependent on the rows of A, which is the wrong conclusion. Right, therefore, I would like to emphasize that we cannot swap the appended row with any other rows for this method to work.